Assalamu alaikum viewers. My name is Varisha Kawal and my registration number is 16TE86. Today is our third lecture of DSP, which is about system and basic signals. First of all, I will explain you about basic signals. Actually, there are two basic signals which are the baseline of DSP, which are unit step and unit impulse. Unit step. Mu of n is equal to 1 when n is greater than or equal to 0. And it is 0 when n is less than 0. As you see from the graph that it represents the unit step graph. Second is unit impulse, which is equal to 1 when n is 0, otherwise it is 0. It is represented by the graph that it gives the amplitude of 1 at 0. So the derivative of the unit step gives the unit impulse. Derivative of mu of n with respect to d of n is equal to mu of n minus mu of n minus 1. If I represent the signal of u of n, which I already told you that it is equal to 1 when n is greater than or equal to 0, and it is 0 when n is less than 0. And the other signal is the shifted version of it. Then when I subtract these two signals, it gives the impulse function, that is the impulse, unit impulse, which is 1 at 0. So this is all about basic signals. Then next is, what is system? System is a process, algorithms or techniques to produce or create other signals. So first important system is causal system. Causal system is if the output depends upon only on the current and the previous version, then that system is causal. For example, if y of n is equal to x of n minus x of n minus 1. In this example, x of n is the current version and x of n minus 1 is the previous version. So, as I already told you its definition that the output depends on the current version and also on the previous version. So, this system is causal. Next example is about non-causal system, which is the system if the output depends only on the future version, that is called non-causal. Next important property on which DSP depends upon is linearity, which is explained as that if the system is linear, it must satisfy homogeneity and additive property, which is also called superposition theorem. Homogeneity. If x of n is my input, and when it passes through the system, it will give the output of y of n. Then if I multiplied my x of n input with a scalar, for example alpha, when it passes through the system, it gives the output which is also multiplied with the scalar alpha, then it is linear. That is, if this input is multiplied some scalar, then it also appears in the output. Then that system is homogeneous. That actually satisfies the only one property of linearity. A system is linear only when it satisfies both the properties, homogeneity and additive property. Next is additive. If x of 1 is the input that passes through a system and gives y of 1 of n output, and x2 of n is another input which passes through a system and gives y2 of n output, then addition of both inputs when passes through a system, it gives the output of the addition of the both outputs. Then for example, if y of n is equal to x1 of n minus 2x of n minus 1, then in this example I have to show that if the system is linear or not. If it is linear, it must satisfy the above two properties. First of all, I will apply homogeneity property, that is, if the system y of n is equal to x1 of n, which belongs to x1 of n minus 2 of x of n minus 1, Then let us consider z of n is equal to alpha of x of n, x of 1 plus n. As I already told you that in homogeneity we have to multiply some scalar with the input. So in this example I consider this as z of n. Now substitute z of n in the main equation, which gives z of n belongs to z of n minus 2z of n minus 1. When I substitute the value of z of n, that is alpha of x1 of n, into this equation, it gives alpha of x1 of n gives alpha of x1 of n minus 2 of alpha of x1 of n minus 1. If I take common alpha, then it becomes alpha of x1 of n gives alpha of 1 y of 1 of n, which actually proves that it is homogeneous. Multiplying the scalar factor if factors out, then it actually shows that the system is homogeneous. Next property is additive property. X1 of n belongs to x1 of n minus 2 of x1 of n minus 1 is actually our first, it gives first output y1 of n. Then if I take the same signal as x2 of n, it gives the output of y2 of n. Let us consider that addition of the both inputs is z of n. Now substitute this z of n in main equation. It gives z of n belongs to z of n minus 2 of z of n minus 1. Now I substitute the value of z of n in this equation. It gives x1 of n plus x2 of n gives x1 of n plus x2 of n minus 2 of x1 of n minus 1 plus x2 of n minus 1. It gives x1 of n plus x2 of n goes to form y of 1 of n plus y2 of n, which is the additive property. So it satisfied both the properties, so this system is linear. Next important property is time invariance. If the system is independent of the time, then it is time invariant. And reverse is time variance, which is if the system is dependent on time, then it is time variant. For example, if y of n is equal to x of n plus 3, it is time variant. Now I explain that why it is time variant. First of all, another example, y of n is equal to x of n minus 2 of x of n minus 1. To check time invariance, we actually add or shift this signal. For example, x of n belongs to x of n minus 2 x of n minus 1 is y of n. So if I let z of n is equal to x of n plus n naught, here n of n plus n naught, n naught is the shift. Now substitute this value of zn here. It gives x of n plus n naught belongs to x of n plus n naught plus 2 of x of n minus 1 plus n naught. Actually, here the shift in the input also gives the shift in the output. It means that it does not depends upon the time. If the shift in the input varies, then there is also a shift in the output. Then that is why this is the example of the time invariance. This is all about lecture 3.